acceleration run. It's a mile from a standing start to the next light, and we have a wall on both sides, so it's nice and safe. We have 2 lanes all to ourselves.
That must be the secret.
This is a V10, 5.7 liter, naturally aspirated. It's in an M6. It makes 628 horsepower and 500 pound-feet of torque. Naturally aspirated, great car to drive, really exciting. Easily goes 200 miles an hour from a standing start in 1 mile and then back to 0 again. Not that I have any experience of doing that, but it has happened. And it also has Dinan cold air intake, exhaust, throttle bodies, all the Dinan parts that wind up in a Dinan car, as well as a Dinan suspension, wheels and tires, and brake system from Brembo on the car. So really neat car all the way around. Supercar level on the lines of a Ferrari 599 GTB. Probably about $100,000 less money than the Ferrari and probably a little faster and more reliable, but on the same level of performance. This is a CNC block boring machine. You write a program here, and it bores every cylinder to exactly the dimension you have. Now, the reason it's important that it's in-house is the type of bit and the speed in which the bit turns determines whether or not the material is going to get damaged as it's cut. Speed's very important. This is what's called an alusil block. It's a high content of silicon in it, and their silicon nodules can easily get torn out by the cutting bit if it's cut at the wrong speed. So we used to farm this sort of thing out years ago, and we had problems with the quality, so we brought it in-house to ensure the quality was right, having it done the Dinan way, as we say here inside the company. By the way, all these processes we started perfecting back in our Daytona prototype engine. We used alusil in the prototype engine instead of using a steel sleeve or Nikasil, because when the alusil is smoother, the piston glides and has less friction, and the rings seal better and there's less blow-by. So a lot of this research actually started in our racing program prior to building the engine for the street car. The technology that we learned in the racing gave us the confidence to move on into the street car development program, giving us the impression that we could make an engine that would last a long time and make a lot of power. In the past, Dinan's been famous for a lot of bolt-on supercharger kits, turbo kits, and we've done some engines in the past, but not very many. But the engine shop, the engine technology at Dinan has progressed a lot over the last 10 years, and we think we're capable of undertaking this kind of task now. So we went ahead and took that technology and applied it to racing to prove that we could. And once we verified that we had that technology down, then we moved into the street cars as well. I thought a little bit more detail on the streetcar engine development program was in order. because such a complex part and there's a lot of interesting things going on here. So I enlisted Frank, who's in charge of the engine program, development and research in this area, to help us along. Frank used to work for Honda doing kart engines back in the old 1,000 horsepower IndyCar days before the IRL came along. He has a lot of experience at high output engines. That's why he works here. We talked before about on the honing machine, how the boring machine actually has to be at the right speed with the right bit not to tear the silicon nodules out of the aluminum block. Frank's going to go into a little bit more details on that. Go ahead, Frank.
One of the things that we found when we had an outside source doing our machining was that the surface roughness was outside the specifications that was called for this type of material. And after doing some research, we made some recommendations to cutter rotational speed and feed speed. And we did some outside testing for quality control, and that actually showed us that we had correctly identified what would have been a manufacturing flaw, and then came up with a good countermeasure to take care of that.
Now to expand on that a little bit, we actually take acetate tape and put it on the bore, and then take the tape out and put it under a microscope. The microscope tells you how much damage there is to silicon nodules on the bore. Then you can refine the boring and honing process to retain the maximum amount of silicon. The silicon is actually what the piston glides on, and we actually make the silicon proud and push the aluminum back as a recess. And this reset also traps oil like you would with normal crosshatch on an iron block as well. Kobenschmidt, who's the folks that perfected this process that all the Germans use on these motors, wrote a manual on how to do alusil. And in the manual talks about making the silicon proud stick out from the aluminum and the trapping of the oil.
So with this type of material, it's the raised silicon allows the oil to be trapped in between each silicon crystal, which is somewhere around 2 to 3 microns apart from each other. So in a standard block, you would have a crosshatch, and that's where the oil resides. And here, the oil resides below the silicon crystal. That was one of our concerns in the manufacturing process and actually risk analysis for long-term longevity of the motor and to reduce possible warranty situations. So we pretty much have all that under control. We log a lot of data on every engine build, serial numbers for the connecting rods, serial numbers on the pistons. We also log the serial number on the crankshaft. So if there is a problem later on down the road, we have the ability to go back and analyze that particular build. We also log, after the engine is built, we'll do a cylinder leak down test, which basically tells us how much air of a given amount is passing through the rings. And on a new build, anywhere from 3 to 5%. So if we have a problem, we can identify it. All of the cylinder bores are measured for cylinder roughness with a profilometer gauge. And this gauge was one of the things that Steve allowed us to purchase to create a QC program for this particular stroker, both the V10 and the V8 program. So the more information we have to record during the build, the less likelihood that we're going to run into a risk later on down the road when we have multiple motors over 2 or 3 years out in production.
This is why it was important for us to bring in the boring and the machining process in-house and buy the CNC equipment so we can get control of this process, because our analysis determined when we subcontract out to other people, they didn't pay enough attention to the process, and this would make the engine degrade over a long period of time, not last as long as it normally would. In addition to the honing and the metallurgical process of the engine bore itself, the parts inside are critical also. The Dinan crankshaft is a billet crankshaft. It's not a welded crankshaft from an existing modified crank, but an actual billet piece, $7,100 a piece. The pistons are made by Moly, which is the original equipment supplier to BMW, and they have a coating on here, okay, which is a ferrite coating, which is basically like a sprayed ferrous material that makes the piston a dissimilar material than the bore. Since the bore is aluminum and silicon, we want the piston to act like metal because similar metallurgical compounds want to bond. If we make a dissimilar metal, they don't want to bond. This makes the engine glide smoothly and not show excess wear. In addition, we went to an American supplier for the connecting rods, the best in the business, Carrillo. They also make our racing rods. Very well-known company, very high-end part, a little pricey like the pistons and the crank, but again, superb quality. We also analyzed the bearing load on the stock bearings and reduced the reciprocating mass of the piston and rod together so the bearing load wasn't increased with the additional stroke, so the bottom end of the engine would last as long as the stock engine. In addition, we also went on to have our own head gaskets made, steel shim head gaskets, in a similar manufacturing process to BMW. These are here made in the United States, so we can increase the size of the bore and have proper sealing on the cylinder heads as well. All total, we spent 2 years on the development of this process, buying machines, analyzing data, looking under microscopes before we were satisfied with the quality. We thought we could match what the original equipment engine was built